Chapter 9.7, Probability. We're going to find the probability of events, probabilities of mutually exclusive events, as well as independent events. So first, we're going to find a sample space. Find the sample space for each experiment. So when you toss a coin, what are the possibilities you could have? Well, the possibilities you could have if you toss a coin is a head or a tail. So that is our sample space. Now, if we toss two coins, our possibilities are you could get a head and a head, you get a head and a tail and then a head, or you can get two tails. So that is our sample space. And then, so I hope you see with the three coins, what you could possibly get is we can get three heads, we could get two heads and then a tail, then we get a head, tail, head, a tail, head, head. We could get heads, tails, tails, so two tails, and then tails, heads, tails, 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 head, and tails, tails, tails. So there is our sample space. There are 8 possibilities here. So here we're going to find the sample space for the experiment. You toss a coin twice and a 6-sided die once. So see if you can list the sample space here. It is kind of large, so see if you can do that. So if you tried it out, this is the sample space. So you're taking the 2 coins, so from example B, and then you're just adding the 1, 2, 3, 4, 5, 6. And so you notice there are 24 different possibilities for that. Let's look at the probability of an event. If an event E has an equally likely outcome and its sample space S has equally likely outcomes, then the probability of event E is a probability of E equals a number of equally likely outcomes over the sample space. The number of outcomes in an event must be less than or equal to the number of outcomes in the sample space. So the probability of an event must be a number between 0 and 1 inclusive. So it could be 0 and it could be 1. So notice here, this little chart here, increasing likelihood of an occurrence. So 0 means it's an impossible event. It cannot occur. B, the occurrence of the event is just as likely as it is unlikely, so 50-50 chance. And then certain event must occur. So let's find the probability of an event. You toss 2 coins. What's the probability that both land heads up? And so what we want, our expected, is we want to get 2 heads. And then so if we look at our sample space from before, right, we listed it already. When we toss 2 coins, what's probably that both land heads up? So looking here, we have 1, 2, 3, 4 possibilities. And so the probability of the event is the number of equally likely outcomes over the number of the sample space. So it's 1 out of 4. Now let's try the next one. You draw 1 card at random from a standard deck of 52 playing cards. What's the probability that it has an ace? So a little bit of background on cards if you don't know about cards is that there are 4 suits. There's hearts, diamonds, clubs, club, and then spades. And then in each suit, there is, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have jack, queen, and king. So the jack, queen, and king are what we call our face cards here. And so that's how we may have 52 cards there. So what is the probability of that it is an ace? So there are 4 aces. So probability of an ace. There are 4 of them out of 52 cards. 52 would be the sample space. And then we could reduce so that it ends up being 1 out of 13. So try this example. You toss 3 coins. What's the probability that all 3 land tails up? And then letter B, you draw 1 card at random from a standard deck of 52 playing cards. What's the probability that it is a diamond? So 3 coins, you're going to want to take a look at this example here on the left and try this out. So looking on the left, you see that all 3 land tails up. That's 1 out of 8 possibilities, right? It's only 1 out of 8 chance. Letter B, how many diamonds are there? So there are 13 diamonds. Thinking about ace through king here, out of 52 cards. So it's 1 out of 4 chance that you could draw a diamond. In some cases, a number of outcomes in the sample space may not be given. In these cases, either write out the sample space or use accounting principles discussed in the previous section. And this example uses the fundamental counting principle. So you toss 2 6-sided dice. What is the probability that the total of the 2 dice is 7? So let's take a look at how many different outcomes there possibly could be. So you have a 6-sided dice, or 6 sides, so that's 6 sides. And then the other one also has 6 sides, so there's 6 times 6 ways. So 36, 6 times 6 is 36 different outcomes that we could have using our fundamental counting principle. Now we want a sum of 7. So let's say if we first toss a 1, our second toss must be a 6. But then if we toss a 2, it must be a 5. 3, that has to be a 4. If we toss a 4, that should be a 3 to total 7. And then a 5, we will have to toss a 2. 6, then a 1. So the probability of the event occurring is the number of equally likely outcomes over the number in the sample space. So that is 6 out of 36, which is 1 out of 6 chance of having a total of 7 when 2 dice is thrown. So try this next example. You toss 2 6-sided dice. What is the probability that the total of the 2 dice is 5? So I would list it out, right? We know the different outcomes is 36, the number in the sample space. And then you can go ahead and list it out. How could you possibly get a sum of 5? So trying this out, you would see that if you tossed a 1, you would have to toss a 4. If you tossed a 2, you'd have to toss a 3, and then a 2, and a 4, and a 1. So there's 4 out of 36 chance, or 1 out of 9 possibility that the total of the 2 dice is 5.